Hello, everybody. My name is Robert Hraniewicz, and I am a data evangelist at Hortonworks. I work and I'm within the community at Hortonworks with Raphael, who's sitting over there. We do, we build tutorials, sandboxes, getting started environments, all sorts of videos and blogs related to Spark, data science, and the entire Hadoop ecosystem. And of course, we run these types of data crash courses and many others during the DataWorks summits. So what is a data crash course? Data science crash course in particular, what we're going to do today are two things. One is I'm going to have a high-level overview of the data science landscape. I'm going to cover some of the machine learning algorithms and really kind of get you started and thinking about some of the ideas. There might be some missing spots. So hopefully it's a very high-level overview of that space. And then around 12:30, well, actually 12:15, we're going to break up for, I'm going to intro the hands-on lab. So we have 5 clusters spin up today. I'm going to have you match up with somebody else. So there's pairs of actually going through the notebooks themselves, launching them, and then going through the lab. And I'll get you started at 12:15. And by 12:30, we're going to basically break up for lunch. And then at 1, I'm going to cover the notebooks in more detail. So you're going to have some time to eat some lunch and then come back and maybe get started on the lab. And during that time, I'll also be able to answer some of the questions informally if you'd like to have some comments, questions, and so forth. With that, maybe a raise of hands. How many of you were at the Spark crash course yesterday? Okay, a few hands. All right, so that gives me an idea. So about 1/3. When it comes to data science, how many of you have done some data science? All right. Python developers? All right, about 40%. R developers? All right, some. Scala, Java? Oh, wow. Okay, that's quite a bit. So the labs themselves will focus today on the Python language, but of course, we can rewrite those labs and have them in different languages such as R and Scala itself. So let's get started. By the way, if you haven't already, make sure you connect to the crash course SSID. You should, no, you don't have the notes today for the password, so it's just DataWorks 18, capital D, capital W. This is so that we have dedicated Wi-Fi and high availability here, so there's no delay. So one thing that I just want to touch, there's a lot of buzz. Last 2 years, a lot of buzz, a lot of hype. Just want to touch what is AI, machine learning, and deep learning, and how they relate to each other. AI is really this bag of technologies, and it's used interchangeably. So some people describe machine learning as AI, but AI is really pretty much everything under the sun at this point. Way back when, AI was supposed to be more this, human-level AI, very intelligent, complex system. Nowadays, AI is by some described as machine learning, but really, AI encompasses things like natural language processing and so forth. But machine learning is the one that we're going to focus specifically on today. So it's really solving a lot of the hands-on problems, known methods, and solutions with specific metrics that you can address. And then there's the deep learning, which is really a subset of machine learning, and deep learning really deals with more complex models that have some hidden layers, and we'll touch on those as well. So the gist of it is AI is pretty much everything under the sun nowadays. Machine learning is really what enterprises and companies work with, and deep learning is a subset of that field. So what are the key drivers behind the AI explosion? Like why now? Why last year? Why pretty much the last few years? One is, as you've all noticed and heard during the keynote talks, is the exponential data growth. It grows really, really fast. I'll touch on that in a moment. But it's also the ability to process all this data, right? You have your Hadoop ecosystems, you have different sorts of tools, you have your Sparks, etc. And you can process both the structured data, that has schema, that has specific fields, columns, and so forth, as well as unstructured. So for example, processing the text data. And of course, we have these faster and all kinds of open source and closed source systems, such as Hadoop, Spark, and TensorFlow, among others. MXNet is on their horizon, as well as I've heard PyTorch. From the comparison, if you were at the Birds of Feather yesterday, TensorFlow has got about 70% of the papers, PyTorch about 20%, and then 10% are the MXNet papers currently published. And of course, smart algorithms. The big one is that there's a lot of buzz about deep learning, of course, but the machine learning algorithms, the big push and the big change was that instead of having a monolithic system, one box with just lots of RAM and CPU, now a lot of these machine learning algorithms that you would use in scikit-learn with Python, for example, were written to be launched in a distributed way across array of systems and compute nodes. And with this hype around AI and machine learning and more data scientists, we're getting more and more accurate models. So I'll skip that because there's a lot of talk about the different use cases. So let's just briefly talk about data. I really like this quote. Peter Norwick, director of research at Google, said that Google does not have smarter algorithms, but more data. So even if your algorithms are not the latest and greatest, just having more data, and especially high quality data, will make a big change in impact on the accuracy or any other metrics of your models. This is a fun one. This is my way of visualizing what 50 zettabytes will be like in 2021. If you were to think of your typical 1 terabyte drives and you stack them one on top of another, just built a really tall tower, it will be from Earth to the moon. So I really like that visualization. That's how much data we'll have very soon. Of course, there's a caveat here that data, not all of that data will be accessible. That's one. Two, not all that data will be in the form and fashion that we'll be able to process and actually have and use it for anything meaningful. So there's just a lot of data at this point. This 2 quotes over last few years, conferences, data is the new oil, but really the training data is the new oil, because when you have the training data, we have data that you can do something useful. When you have labeled data for supervised learning, when you have data that's been cleaned up and so forth, that's really what's useful for your data science exploration. And another quote that I like, the effectiveness of AI technologies will be only as good as the data I have access to, and the most valuable data may exist beyond the borders of one's own organization. And this touches on some of the keynote talks and keynote topics where some of the data that you might have in your enterprise, you might be required, or you might look into other data sources. So data marketplaces will be probably yet another topic they'll be surfacing very soon, of how do you get access to additional data sources for your purposes to make sure that your models have even more predictive power. This is another image that I really enjoyed. I saw it. So you got your AI and deep learning at the very top, but what do you need to actually get there, right? Many companies, are already started on this path of, they've collected the data, they've stored it, they have some of Hadoop store system. The next step is, where you actually clean it, you do basic processing. Then you start to doing some A/B testing, some simple machine learning algorithms. You might be spinning some, ephemeral clusters and short-lived clusters to do some explorations, or perhaps some small explorations on your local machines. And then you're getting to this more high-level enterprise-level systems of where you're actually processing large data sets. One of the key points, of course, is to remember that there's the data science lifecycle. It all starts with the problem definition, and like you've seen in the pyramid itself, there's the ETL, or the extraction, transform, and loading. Looking at the features, what are the key features or variables for your in your data sets for training algorithms. Of course, the learning part, the machine learning that we'll be doing today. And the key part is, of course, model deployment and model management to make sure that the models perform as new data arrives, as the environment changes. So here, this is one of the images that I've used quite a bit, but it really is the essence of talk. You see the machine learning, which is really just hacking skills or computer skills with some math and statistics knowledge. A lot of the statistic methods nowadays are called machine learning. A lot of statisticians call themselves data scientists because it's very similar. And that essentially is machine learning, where you have the statistical background, the mathematical background, plus your computer skills, and you can combine that. As you can see, the machine learning in and of itself is agnostic of the actual field that you're in. So once you add the actual substantive expertise in your field, when you actually know the data, when you know the area where you work at, this is where there's the definition of what data science is in of itself. So maybe very briefly, what is a model? Just wanted to point that out just to make sure that everybody's on the same page. So really, it's about just fitting a model to the data that you have, and that process in and of itself is model training. So the simplest one is just fitting a line to a number of points. There'll be model training, as you recall. Let's see if my arrow works actually. You would train the simple line for these data points and fit this blue line over here. You would just have your function, y equals mx plus c. After you train, your model is a very simple function where the best fit after there's quite a bit of complexity underneath. Of course, for things like linear regression, you would have 2x plus 5. And then, of course, you have your input that's transformed of the function. This is your model function, and there's the output. So that's one of the simplest models that we can think of and touch on. So some of the algorithms, I pull out a lot of some of my favorite cheat sheets. If you're coming from the Python world, there's the scikit cheat sheets. Microsoft's got a pretty cool one for their environment, SAS, and a few others. So if you need something to quickly look at and go into slightly more detail as far as like what algorithm should be using in which case, there's quite a few examples out there. I'm going to start with something even simpler, just a starting point depending on what you want to do and what do you want to use it for. So we're going to cover classifications, collaborative filtering, regression for supervised learning, clustering for unsupervised learning, and dimensional reduction to make sure we only care about the relevant data or relevant features. So let's start with classification. Some of the key algorithms that are worthwhile mentioning, logistic regression, which is good, and it's a fast training linear model. Classes are expressed in probabilities. Support vector machines, by many still described as the best supervised learning algorithm. It's very effective. It's more robust to the outliers than log regression. Handles nonlinearity. Random forest, which we'll actually have in the lab itself today. It provides fast training, handles categorical features, so different categories. It doesn't have to be just numbers. Does not require feature scaling, which is really good, so it doesn't require normalizing. And captures nonlinearity and feature interaction. So if there's some nonlinearity in your data, it's also very useful. And finally, naive Bayes, which is very good for tax classifications and assumes independent variables. And what I mean by that is that allows you to look at the text and just look at the specific keywords and then have the probabilities of these keywords contribute to the essence and classification of the text. For example, if you're looking at classifying into different groups. This is really cool, so I'm going to go briefly into a decision trees. So there's a very cool visualization that I found, and I've been talking about it. So if you're just starting playing with different models. So this is a visual intro. By the way, I'll have all these links in the lab Google spreadsheet that you'll have access to. So during the lab, you can copy all of them, and you have access to this. So no worries. So let's just focus on this one. Basically, this is, how many of you have seen this one, by the way? All right, one person. Fantastic. So this one is just looking at how to distinguish the house prices between San Francisco and New York City. So some intuition, as you probably can imagine, a lot of the houses on this hilly environment in San Francisco will be placed quite high compared to where a lot of the houses are in New York City, and what is the ultimate height and elevation. So you can see that the most houses in New York City are about 240 feet, which is not that high, which is about 73 meters. And a very basic classifications would be to just split them on that height. Go ahead. Oh, sorry. Yeah. Pardon me. If you do not see something, do let me know. Is that better? Fantastic. Much better. Okay, cool. Yes. Definitely. If the text is too small or something, just let me know. I get carried away as I talk. So another way of looking at it is, if you add the different splits, there's the height, but also, for example, what is the price per square footage, as you see over here. But still, there's this area, this white area over here, where no good boundaries can be drawn. So as you can see here, we will capture all the green points, which would correspond to San Francisco, and all the blue points right here. So now we have two boundaries, or two cutoff points. Within the decision trees that we'll talk in a second, these are called the different forks. But of course, as you add more categories, such as what's the elevation, the year built, number of bathrooms, bedrooms, price, square footage, and the price per square footage, you can get more better boundaries that you can draw. Another quick way of looking at boundaries, if you look at the histogram, you can see what's the majority of houses. So just because there are houses that are very high in San Francisco, they have tall elevation, the actual number of those houses in general is very small. So the distribution of those houses based on elevation looks like this. So you could more naturally draw a fork. You could choose your fork at 242 square foot right over here, and that would give you a 63% accuracy. But of course, with the machine learning, you could go back and forth and kind of find better forks to see if you get better accuracy. So if you go all the way to the left, you get 56% of correct, but of course you can get a lot of false positives. And then the best split determined by machine learning, because automated would be somewhere around 92 feet, which would give you about 82% accuracy. So this could be our first split, or our first fork. And then with recursion, we could look at other data. So what will happen is there'll be different forks and different splits, and then depending on which side of the tree you end up, there might be other categories that will be more useful to actually make the split on as the next one. So for example, on the right, we split on the price itself, and on the left would be the price per square footage. So as you grow the tree, you have different categories and the different forks as you go through the process. And then eventually, you have your trained model. So if you were at my Spark crash course yesterday, I've mentioned this quite a few. So you're making your split on you're training on 80% of the data. It's a little bit slow right now. So let me go faster. And that should be, of course, 100% accurate if you run through the model, because the same day. The cool part here is that you can actually trace individual points. So again, this is very interactive, which I like a lot. And then, of course, there is the reality check that you will do if you're a data scientist. So now we'd use the remainder data that the algorithm has never seen. And if you run the whole thing, you would have almost 90% accuracy. There's some errors due to overfitting, and you could do some more things with the data, but hopefully this is a pretty cool example. All right. So then, of course, you have the regression, which focuses on predicting a continuous value output. For example, predicting the house prices based on number of bedrooms. This is a very easy statistic. Essentially, you're just fitting a line to your data points. Clustering, in this case, the animation is a k-means clustering animation. So you could maybe looking at how do I find groups of friends, and this is unsupervised learning, so there's no external labels that specify what these where this data belongs to. So basically, in this case, the algorithms figure out this on itself. And what's useful to point out, and I'll mention this again later, is you have 4 cluster centers that they have to figure out. Basically, what you randomly specify where they start, and then they converge and basically find these major clusters. And the number 4 of clusters, one part of actually doing your data science prep is sort of saying like, okay, there's about 4 clusters, so my hyperparameter or my external parameter to this model should be number 4 clusters. Of course, maybe you can try 5 clusters and see if that's better performant, but in this case, 4 clusters looks pretty good. Of course, there's then collaborative filtering. So essentially what you do is you're filling out the missing entries is in a user item association matrix. So user item in this case, whether it's Netflix for movies or Amazon for recommending additional items or books based on what similar users, similar customers have purchased. This is something that you could use in production to have that kind of recommendation systems. And of course, finally, dimensional reduction, very useful technique for reducing the number of and finding the number of redundant features and variables. It's also a very popular technique for removing noise in images by selecting only the important and critical features. And what happens here is that it essentially looks at the largest variance, right? This is your first dimension, and then the second variance is this perpendicular axis over here. This is your second dimension. It looks at the dimensions and finds some of these core components and features, and then combines them for these new features after applying this. Again, what is useful? So, for example, if you have your data sets in miles per hour and kilometers per hour, they are linear dependent, which means that they don't give you any new information. So when you have a car speed in miles per hour and kilometers per hour, you could easily remove one of these variables or combine them to and not lose any information. Of course, there's more algorithms, and as you go forward in your data science cycle, for example, classifications is a great XGBoost library or extreme gradient boosting, which essentially means that boosting in this case is taking weaker models and combine them, so essentially an ensemble of weaker models to create a much bigger models. And there are some others like I've seen LOAS being used for some local regression, and it looks different on how these algorithms are implemented. Of course, then you go into deep learning, which we're not going to cover in this crash course much. But for example, you have your recurrent neural networks, which don't have a fixed input and fixed output, but have these memory units, and it's very useful in that sense. And then your convolutional neural networks, which are very similar to your classical machine learning networks, which you have fixed input and fixed output. And of course, other algorithms for more accurate model prediction. All right, so let's quickly touch on deep learning. So as I mentioned before, one of the key determinants in deep learning is that you have these hidden layers. The way these layers work is basically you have your inputs and different weights on these inputs. These weights are determined as you train these algorithms. The transfer function is basically a summation function, and when there's enough of summation of enough inputs, kind of like in your neural brain, that's why this idea of neural networks comes in. If you have enough spikes and you have discharges, so this is actually even a simpler visualization of it. If you have, say, in this case, more than 50% of a threshold, then the binary output would be yes, and that output would then be passed. So from your input layers across these hidden layers, they get activated, right? You get summation functions, and then if there's a spike, it would pass in the spike to all the other nodes, and then they would spike farther if there's enough input. And of course, what happens is when you have your outputs and you have your expected values that you're looking for with your labeled data sets, then you could train and adjust and readjust these weights until your algorithm performs in expected fashion. So very briefly, I'll show you this one. How many of you have seen the TensorFlow playground? 1, 2, 3, 4, 5. Okay, very cool. So for those who haven't, yet another great visualization, and again, the link will be there at the end. So this is a great way to play with some of these neural nets. So if I spin this one, Oh, yes, thank you, thank you. Please do point that out. I don't know why that happens. Okay, boom. So yeah, so you can play with this, and the cool part is it can easily add, additional hidden layers. You can change your regularization functions. You can change your activation functions. ReLU is the very popular one. Basically, it's 0 until you reach 1 point, and from that point on, it's a linear activation function going up, one-to-one mapping. So there's a way to just play around and see how having different layers, having different function affects your model. But this will be at the following deep learning crash courses that we'll have in the future, and we'll go more in depth. But there's a lot of cool problems that you can play with and sort of see how some of these models converge and what happens when you talk about deep neural nets. Again, this is another cool cheat sheet that I found. It's just neural networks. You have a lot of different construction depending what you want to achieve. It's good in the sense that it's pretty thorough in what's out there, and if you're just starting with neural networks, I highly recommend that you take a look at this one. It gives a bit more information of what the structure is and kind of intuitive feel for it. There's a cool comment that I found about deep learning in and of itself. Deep learning is, it's great at language tasks, image classification, speech translation, and so forth. And it did very well at playing games like chess, Go, and even more recently games like StarCraft. But it's less performant at traditional machine learning tasks such as credit card fraud, detection, asset pricing, credit scoring. So that's something to keep in mind. And, you have to really look at what is the area that you're applying to, and oftentimes you'll see that these much simpler machine learning models will perform much better. The actual train time will be much shorter, and generally data sets won't be, the actual size of the data sets won't be needed to be as large. Another top 10 challenges that you'll see in deep learning, which is worth mentioning before we move on. One thing that, unless you've aggregated a lot of data sets, you might not have enough data to actually train them. For example, the ImageNet that has been posted, it has 9 layers, 60 million parameters with 650,000 nodes from 1 million examples with 1,000 categories. It's a pretty massive data set. And of course, the 10 challenges, again, to it is that it's data hungry. It's shallow and limited in capacity for transfer. So once you train models on a specific example, which is actually a great example about the AlphaGo, there was a question, actually, interview with the developers of AlphaGo. Remember when the AlphaGo actually won with the champion of the Go game, and there was a specific board, I believe it was like 20 by 20 size, and there was a question what would happen if you've decreased the size of the board by 1. So say it's 19 by 19 or 21 by 21, and the answer was very quick that basically the AlphaGo would completely fail. It was only trained on a 20 by 20, whereas the human player would probably be able to quickly adjust and still perform relatively well. So that's one of the ideas of where deep learning is still today, that it doesn't have this transfer learning capability. Of course, a lot of researchers are working to solve this problem, but we're not there yet. Other thing is, it's not sufficient transparent, so it's complex to analyze. So again, a lot of tools are being built to sort of get additional insight of what actually happens in these models. Cannot distinguish causation from correlation and presume stable world. And of course, difficult to engineer with. One thing always to keep in mind, I like this graph as well, is we've discussed your conventional machine learning. What's the amount of data needed to have this performance? Generally you have pretty high performance of most problems of this one, but as you get to this, higher and higher accuracy, you need a lot more powerful system, a lot more data. And again, one core thing to remember is, on one hand you have your deep learning networks if you spent enough time, if you have enough resources, you have a big enough team, so compute, storage, right, because lots of data, then you might get a very high accuracy. But the explainability, again, is quite low. On the other hand, if you go to the decision trees, as you saw, you could visually actually inspect what happens at the different forks at different levels. You have high explainability, but perhaps that prediction accuracy won't be as high. So this is kind of like a way of looking of where different models are compared to accuracy and explainability. For some cases of, for example, determining whether a specific individual is could be accepted as, for example, for this specific loan or not. This might be an important factor where you have someone inspecting the machine learning algorithms to actually be able to tell this is why the decision has been made, right? So with decision trees, for example, this could be easily made because you can actually follow the path of how the decisions have been made, and you could adjust them if there are some biases especially in the underlying data or perhaps how the algorithm's been made, versus, again, the deep learning networks would be much more complex to actually analyze. One thing worth mentioning, and it still touches on deep learning, it's quite easy to fool deep learning models. Here's a sticker that's been generating from some of the intermediate layers of these deep learning algorithms. So to us, this sticker it looks quite nonsensical. You can sort of tell that it is actually a silver toaster. But what happens is, here if you have this classifier, it would be almost 100% confident that is indeed a banana, but if you place the sticker next to the banana, it suddenly seems to be a toaster. To us humans, it's still a banana with some random sticker, but these algorithms get fooled quite easily. There's, of course, a lot of work to get this fixed, but it's something to always keep in mind. Of course, one thing, and this kind of touches back to the GDPR keynote we had, is making sure that the data sets are clean, that the data sets, that we know where the data sets have originated from, that the data sets haven't been hacked, haven't been changed in any way. Sometimes even changing the pixels, individual pixels in these images could result in having a completely different classification by the algorithm versus the humans, so it would still look like a banana. In the automotive, this is actually very important. What if you place these stickers on stop signs or any other signs, and suddenly instead of a stop sign, this becomes you're free to go, or some high speed limit, right? This could actually cause quite a few accidents. So we might see some hackers trying to hack these systems, but of course there's a lot of work to try to prevent that. So let's go over this journey again. Anytime you go through this journey, of course, there's some sets of questions you should be asking. Whether the problem that you're using is it specific enough? Can you get a clear answer? Is it measurable? Right? Is it quantifiable? Data-driven? Actionable? Can you actually do something with it once you have the answer? Is it realistic? Do you have enough resources? Do you have enough manpower to actually develop these algorithms and get something out of it? And of course, very important, is it timely? Would you be able to deliver the actual solution in a meaningful time? Data preparation, this is another critical component. For example, if you're just looking at the different states in California, you've got to make sure that you set on a specific version of it. A lot of the algorithms will think that these are actually different input variables. So you want to make sure that once you see the different categories, it converges into a single one. So it's just a single category for those. So there's the data analysis part where you actually audit for anomalies. You then create an intuitive flow of what actually happens as you transform these data, you clean these data. Validation to actually make sure that the data is correct. Transformation, where the prep takes place, and a backflow of clean data. And all of this, you have these numbers going between 60 to 90% of this work is actually just the preparation. So it's good to have, as you build out your data science teams, it's definitely very useful to also have data analysts who can help you with preparing this data. On feature selection, very briefly, so when you're actually creating the predictive model, or features, also variables or attributes, one is if you can have less features, that simplifies the model. It's also easier to interpret what is going on. Generally shorter training times and hence generalization by reducing overfitting, another very important problem. And there's one question that has been raised quite a bit. What is the difference between dimensional reduction and feature selection? When you have dimensional reduction, you create new features by combining them. And with feature selection, you either include or exclude ones without changing the underlying features. Make sense? And again, hyperparameters. So these are the higher level parameters. You define them, for example, in the decision trees, how many different layers you would have in the decision trees themselves. They cannot be learned, so you have to specify them as yourself. So one of your tasks as a data scientist would be to actually figure out what those hyperparameters are. There are tools to help you figure out what the best parameters are, so a lot of these things are being automated. And as you look to evaluate some of the useful values, and most of you probably aware of, what are the residuals, what is the R squared, what is the root mean square error, some of these things as you look at to evaluate the actual models after they have been trained. With that in mind, there's no simple formula for good questions and how you go about asking those good questions that I've mentioned in the beginning on general guidelines. As I said, the right data is generally better than lots of data. And again, for a data scientist, someone who is in that field, it's understanding relationship matters. So again, if you were to summarize in a slightly different way, there's different steps, right? You ingest and enrich the data. You then clean, transfer, or filter out. You select or create new features, such as dimension interaction, feature selection. You have your training sets, the learning algorithm, then you have your hypothesis, which in the mathematical realm, or your model, the machine learning model. Then you evaluate the accuracy, and you repeat this cycle. What happens in model training? So for example, very quickly, if I had my scattered data with my labels and feature, and this data to your right would be the actual data points. In this case, like I mentioned previously, what is model training? I would actually discover with, in this case, just these 3 lines of code. I would specify this is my linear regression, and then fit the scattered data from the previous screen, get my coefficients intercept, and then plot it. So really, that's all there is to a linear regression. Of course, all there is to it. This is a very high level. This is what you'll be interacting. Underneath, there's a lot more complexity that goes into actually determining these things. With, when you have 2 features, then you're looking at 3D images. So for example, plotting here a plane. And let's go quickly over Spark machine learning pipelines. If you were at the Spark crash course yesterday, I talked about this, but basically the API allows you to create these pipelines, which are very useful because you can specify different steps that we'll have to take, and you lay it out as a pipeline. At the end, of course, you would specify your a final algorithm, in this case linear regression. And in the Spark case, which also comes from the Python world, you have this fit, which is used for actually training the models. And then once you have the pipeline model itself, you would apply the transform function for the actual prediction. And another thing to point out is we're actually dealing with data frames. Again, if you haven't attended the Spark crash course, data frames are very similar to Python data frames. Or pandas data frames in this case. And it's basically passing this data that's got some structure to it, and that's how the Spark machine learning pipeline is built. Some very simple code right here. What we have is, again, random forest classifier. You've seen the decision trees. Random forest is just an ensemble of decision trees, and that's something that will be used in the lab itself. Here what we do is we specify the number of trees, so in this case using 100 trees. There's the pipeline with the different stages. For example, indexers, parsers, hashing transformer, and a vector assembler. And at the end we add the actual random forest classifier. In our pipeline right here, we apply the fit on the training data. So your training data will be some 70–80% of the data that's not being used for the model training. And then once you're done, once you have your model, you apply the transform functions on the test data to actually test the model. So now it will test on data that it hasn't seen before. Yes? So in this case, yes, so the fit is a general function that will work with all the models that are specified in Spark. So the question was whether fit would still work with the random forest, and you'll see in the code the same example. So let me briefly touch on the DSX. This is another image of, this is basically what happens in your data lifecycle. The actual machine learning code is very, is a fraction of it. This was part of the paper, Google NIPS paper. So then when you go into data lifecycle, there's a lot of these different tools that will be used for actually partaking in this. A lot of these are listed as the open source tools. You got your Sparks and Zeppelin for feature and extraction, right, for the environment, etc. You got your different languages for actually learning, whether it's Python, Spark, Scikit, library, TensorFlow, MXNet, etc., and then model deployment. The one thing about model deployment and management that we're going to go over today is using the data science experience. This one actually sits on top of HTTP, and I'll tell you in a moment how it communicates with the HTTP cluster. But the part of it that is very useful is that it's got these several pieces. One is that it actually allows data scientists to effectively collaborate with each other. So for teams, it's a very good tool. It's got a lot of the very popular notebooks integrated. So Zeppelin, Jupyter, and RStudio. And of course, it uses the Apache Spark as well. And it's got a lot of the libraries, for example, Conda libraries, pre-configured and pre-installed on as well, and distributed in the nodes as you push them down. So that's very useful. Yesterday, we've actually used the Zeppelin notebook. So today, we'll use the Jupyter notebook because I know that's very popular with data scientists. Still, model management, that's the key piece. So once you actually have built your model, you've tested, you've looked at the accuracy of the model, then you want to manage it. You want to make sure that the model still performs to the level that it was designed to perform, that the accuracy or area under the curve is not becoming lower. And of course, a lot of the enterprise features, so security, governance, and of course, scalability. So from a high-level perspective, what happens here is we have the data science experience. It communicates via a REST server called Livy. For Jupyter, it's using the Spark Magic, and Livy for Zeppelin is just going straight to Livy, and then it pushes the jobs to the Hortonworks data platform. All right. So we got about 15 minutes. Oh, we got a little more time. So for those of you who are watching this recording, if you'd like to get the slides and the presentation that I'm talking about and any other information, this is the link for you to go to. For everybody else right now, if you want the slides and the presentation, you can go to this link. This link will also be available from this link, which is the link that will take you to the actual Google Sheet with all the information that's provided in this classroom. So I'll let you all take a picture of this if you need it, or just type it in your browser as we speak, because this will have the information for the labs themselves and the instruction of how to get started with the lab. Anybody else needs any more time? Okay. So if you go to this link, that was bad. Okay. So there's two pieces. At the top is the getting started. So if you click, there's the actual Google document that gives you instruction of how to go and get the notebook for the class imported into your cluster. If you would like to leave your email and get the presentation or some more information, subscribe to the newsletter, or just some comments and feedback for this session, then it's the Google Form link. It's also in the getting started. And here what I have are 5 clusters. So make sure you combine in pairs, so you work together, because we have a limited number of sign-up speeds, although we might be able to do some individuals here. And make sure that you scroll down so you're not all on one cluster as you spin up the jobs. Put your name next to it, and then what you have is a link over here. For example, for cluster 1, you can just copy and paste it into your browser, and then use the user and password that's next to it. Please make sure not to launch any other notebooks at this time. Just focus on following this one, as every notebook, as every container, as every pod that's being spin up for you takes quite a bit of space, about 5 gigs of memory. So we want to make sure that the clusters are not overwhelmed. Later on, as we get towards the end, I'll let you to explore other notebooks that are pre-installed with DSX. But at this point, to make sure that everybody's got a good experience, please make sure that you only launch this one notebook and don't launch anything else. If there are issues, do let me know, and I'll walk around, especially during the lunch, make sure that everybody gets started, and then probably we'll see, maybe around 1 o'clock I'll go over the notebooks themselves in more detail if you still want to hang around. Other thing, as I mentioned, are the links over here. So if I was going a little bit too fast about the models and you would like to rewatch it, there's a 5-minute video I've recorded previously from other crash courses that goes around these basic models. There's the trucking demo, which basically describes the lab that you're going over today. So here's a blog that I wrote. It's after, sorry about that. Yeah. So this is a trucking demo lab that basically describes the lab that you'll be analyzing here today, going through the different life cycle, and also there are videos attached. Oh, one moment, I'll be right back. I'll get back to you in a moment. Yes, there's a valid question there. We'll see how well it is as I look at it. But let me just mention this one before I move on. So this is the blog that actually describes this entire demo with some of the videos recorded. So if you need to look at this later on, you need to review it to kind of get a feel for this entire notebook. Here are the different steps. With this lab, which we're not going to cover today, there's also a NiFi component attached. So after you actually train the models in a NiFi, you can have a streaming application that goes to the REST API and accesses the REST API endpoint, which is a trained model, to actually do real-time prediction. So this is an actually very cool blog that I highly recommend for you to check out. And the actual notebook itself for this video is attached here in resources as well. Let me just touch on a few more things. If you have any questions, what is not linked? Yeah, so the trucking demo, the notebook itself, is basically so I'm saying that this blog describes the trucking demo that you'll be going over today. So if you want to follow up and redo the lab or rewatch some of the videos, or if you want to do it on your own time because you want to run to some other sessions, then feel free to do so. But basically what I'm saying is, if you want to follow up after the lab itself, this is the way for you to go and watch it. And this is the link. Just three or four more links that I want to describe before I move on and actually go through the different steps of how to get started. If you have questions about anything, there's the Hortonworks Community Connection, or HCC, which is essentially Stack Overflow for big data science, and many of the stream technologies. It's very useful. A lot of our solution engineers reply to many questions or support, and of course the wider community. There's many assets, and I've did a quick demo yesterday. And of course, the other introduction that I've shown you today, the visualization to decision trees or the TensorFlow playground, all these links are over here. So I see that most of you have spread out across these clusters. Very good. So let me go to the actual document over here right now. Okay. So if you have any errors, feel free to proceed. It's safe. It's just we're not hosting any certificates on these clusters. You should be able to go through this one quite quickly. So the point you were making was on the create notebook. Okay. So let me scroll down. You can't copy this? Can anybody else? Okay. I don't know. Try disabling an ad blocker, perhaps. I'll come to you in a moment, but this is the link. If you need to get to this link, you can also search my GitHub repo. For the instructions, yes, but the link you should be able to copy. Oh, is that what you're asking? Apologies. Yes, yes. So this is disabled, so it's not downloadable, but all I need you to do is just copy this link and import this to use it to import the notebook. Does that answer your question? And can you do that? Can you try a different browser? Maybe there's something with the browser. Which browser? All right, I'll be there in a moment. I'll help you out. Let me just make sure that everybody else can get in this one. And again, at the end, feel free to fill out that form over here that I mentioned. And when you get started, you should see this screen over here. So basically, you should get to this point when the actual notebook is important. Since there's quite a few people in each cluster, it might take a few moments. But once you import it, you should be good to proceed with the lab. So it's right over here in getting started. These clusters will be up to about 9 p.m. local time. So throughout the sessions, especially once we get closer to 2 p.m. After that, feel free to have fun with it. One thing I want to show you, because there might be some issues if you start the notebook and then somehow you import yet another one, please do monitor your environment. So in the top left corner, let me scroll down. Shoot. Okay, right over here. In this drop-down menu, once you get the notebook, there's the environments. And when you click this environments, which is a very important part, so this way we can all work in unison whenever I log in. There'll be a list of the different jobs that are running. So if you're running more than one, please stop the other one. This way, we only have one at a time. So if later on you're running other notebooks, you're testing, because there's quite a few, there's about 30-some notebooks that are pre-packaged with DSX as demo notebooks, make sure that you kill the other ones and run only one. So this way, everybody can have a whole day of fun and exploration of or whatever else you want to do. I think I have to refresh this. Okay, there we go. Yeah. So you can see that right now I have just one running job. So this is important that we all manage our user resources in a responsible way. Let me get back. Was there anyone that was not able to get to this point? Okay. So what I'll do right now is I'll walk around, make sure that you're all set. At 12:30 is lunch. So maybe because we've actually finished a little bit faster and earlier than I thought to get to this point. So what we'll do is 12:30, will 15-minute break be good enough for you guys to grab some lunch, some main dish, and then bring desserts, whatever else here? because at 12:45 I'll go over this notebook in detail over different parts, and then if you want to stay or you want to go to different sessions, then you'll be free to go. Sounds good? Okay. So I'll walk around. If you want to get started, start with the notebook. All the instructions should be within the notebook itself. Basically running the cells. Each cell, the easiest way is to just go Shift and Enter to run each cell or paragraph. Or just you can go here to the cell to run all cells as well. That will run all the cells, but I highly recommend that you go one cell at a time to sort of try to understand what goes on and definitely read the instruction in the background. I'll also go over this, but for now I'll leave you to it while I walk around and make sure that everybody gets to this point. For those of you that want to take a break now, I'll be seeing you guys again at 12:45. Feel free to bring your desserts, cokes, coffees, whatever else you need. And then I'll follow up with this one, and then a few slides at the very end if you're still here and not asleep, and then that will be it. Sounds good? All right, cool. So I'll walk around to everybody that still's got issues and make sure we can get those resolved. So there's one thing I wanted to point out. Let me get this moved out. So we've got this version 113, and for some reason, you'll get this no such file or directory when you actually run this paragraph over here. But the file does get downloaded, because as you go down, you'll see that the actual trucking CSV files do get downloaded. So there's some bug with this release when you use the wget. Not sure what exactly. It seems it gets downloaded here, but then does some complaining over here. So that's a minor thing. But then when you run this paragraph to actually put this in a data frame, as you can see, the file is there. So don't worry about it. Thank you. All right. So let's get started while everybody else is flowing in. So all I'll be doing is I'll be going through these different cells, these paragraphs, and in the end, hopefully show you a working model that you can play with. So what you'll see underlying each of these cells and nodes is, if you double click it, it's just a markdown. In Zeppelin notebooks, you would specify an %MD for markdown interpreter. Here, by default, it assumes it's a markdown for this type of text. So what we're doing is we're going to initialize, import some of these files. Again, if you have this message, it doesn't mean that the file doesn't exist. There's just a bug here, and I'll point that out to the director of DSX later today. So what happens here, we actually use Spark context, which has been pre-initialized in this notebook. By the way, can you see it all the way in the back? Sweet, okay. And then we're going to show 5 elements of this events file data frame. If you look into the IoT tracking demo CSV file, you'll just see basically headers on top, and then all the data, which then infers all these headers for different columns. And of course, you can see the data that is in this data frame. One more thing to note here is, and we'll get back to it later. So we have a total of 649 elements in this data set, with 174 violations and 475 no violations, which will affect and some of the analysis at the very end. So the data set is slightly skewed to having mostly no violations. And this is important, especially when you have larger data sets where the skew is even larger, right? So one thing in, for example, fraud detection, the problem is, mostly there's no fraud, and the actual data sets, when their fraud is detected, or where, in this case, a violation has been committed, you don't have as many training examples, and only the machine learning algorithms will learn when you have those specific training examples. So knowing what your data set looks like is critical. I should probably go back and actually preface what this problem is about. Hopefully most of you read about it, but this is a case that we've actually demoed live, and as I mentioned, it can be connected to work with streaming data sets, and I thought that especially in Germany this would be a useful example because a lot of you I know actually are interested in IoT. So it's a great example because it's IoT plus data science. You train the model, and then with the IoT the tools such as NiFi, you can simulate the traffic and actually score in real time to see if a violation would be committed or not, or basically use this predictive model. So in this case, basically it's a trucking company, and what you want to see is whether violations have been committed by a driver. So a violation could be, you're swerving, you're going too fast, and things like that. And that's what kind of violation. And depending on where you are, what are the weather conditions, how many hours the driver has been driving, or equivalently how many miles the driver has been driving, predict what's the likelihood that a violation will be committed. So then, in practice, what happens, you can have, say, a dashboard and your predictive model and say, there's an alert that goes up to the, say, central repository, central office, and it says, you should probably call this driver, or the driver gets a text message on his phone or some kind of other alert, says you should probably pull over, get some rest because you're at a high risk of committing a violation, of just swerving or doing so forth. Actually, this goes back into what you've described. This could actually go even more detail of having driver-specific parameters, or basically training models for specific drivers based on their previous driving history, and having these models even being more accurate, being targeted for these specific drivers. Say this driver swerves and commits some kind of violation, over speeding or tagging other vehicles too close, and perhaps he should pull over and take some rest, versus other drivers that only have this kind of higher risk after 50 hours or so. In this case, we're taking all the drivers and all the different data points, and what we're trying to do is basically find out if we can have some models that have this predictive ability. So then there's some data wrangling and basically showing you what the data types are underneath. You can see there's there's a lot of strings, and then some basically you have some strings, and then what you have to do is actually do some type of conversion. So in this line we're basically specifying, casting these values to being strings, integers, and floats. As you see, this is very relevant to the models themselves. Then of course we're doing some feature engineering. We're converting our data frame to pandas. If it was a really large data set, you would probably want to sample it and then convert it to pandas. We're converting to pandas for quite a few visualizations that are in this notebook, and I'm going to touch on all of them. In this case, we have our pandas data frame. And again, the pandas data frame is very similar to Spark data frames. Go ahead. Yes, exactly. But for the purpose of this notebook, to get some of the visualizations, we're using it. In practice, you would probably sample that data, sample it on Spark, have a subset of it, then convert to pandas for visualizations. We're only doing this because we want to have some insight into the data set. In practice, this would probably not work for much larger data sets, because if your driver and your local machine where you're pulling this data isn't large enough, that would actually crash it. So very good point. Yes. So for example, if you look, and I'll share this with you, the notebook from yesterday, it was all Spark-based. So you have all the histograms, all the data preview. I just wanted to show you some more advanced visualizations. So for example, a lot of the visualizations that I've showed yesterday in Zeppelin, they were pre-built visualizations, so it was easy. In this case, my colleague wanted us to share some other stuff for the purpose of this crash course focusing on data science. So very good points. I'll actually make some comments for the next data science crash course, making this very explicit. Excellent point, guys. Thank you. So what we have here, I want to make sure that you see, so these are the different types of violations that be committed. So lane departure, overspeeding, unsafe following distance, so basically being too close to another car, or unsafe tailing distance. What we'll need to do is basically convert them to the same group. We're going to register a temporary table or a temporary view. This is for SQL queries, which we're not going to be doing today, but they could be used for using SQL syntax. So again, what we're going to do is have event types to be either 1 as violation and 0 for normal. And two other things, we're going to convert them to numbers as well. Is the driver certified or not? And what's the payment scheme, whether it's in hours or miles? The certified and not certified will come into play as you will see shortly. So I'm going through some more transformations. So now, as you can see, all these values have been transformed to 1s and 0s, floats, and in integers. I'm not going to run this because I've already run this before, but this is my correlation matrix. So the point I wanted to make here on this correlation matrix, as you're exploring the different features, as you're exploring how, what's the interaction between. One thing, of course, you'll notice is that on this diagonal axis pointing down, it's basically feature to feature. So event type to event type, there's going to be, of course, 100% strong correlation. But what's more interesting is the event type, whether that indicates a violation or violation, and looking at other features. So for example, you can see that there's a negative or inverse correlation for event type and is certified, meaning that is certified generally indicates or lowers the incidence or violation. So this is a way for you to look at what's causing and what contributes strongly to the outcome of these event types. And that's just looking at the data set. That's not even training any models at this point. Then with the lighter colors, you can see something that contributes slightly or not as strongly. So for example, here we have the weather condition. So is foggy and is rainy, and I'll point on that at the very end as we're looking and playing with the models, the trained models, strongly correlate with a risk, a high incidence of a violation being committed, and is windy is, not as strong an indicator, which sort of makes sense, right? When you have rain, when you have fog, the visibility is much worse. That would make sense that there's a higher probability of some violation, and windy, I mean, it's just slightly harder probably to hold on to the steering wheel. So then we can go and visualize this in this pair plot, which isn't that interesting just because most of these are categorical or binary features. But here what you can see, if you're wondering what this is, this actually corresponds to the longitude and latitude. So actually this one, come on, yeah, this one right over here. So essentially this is sort of the driving patterns of these users within the data set itself. That's why it looks sort of weird. But it doesn't really give us that much information. Longitude and latitude is basically the location points at which data has been collected. All right. So if we look at the data frame histogram, you can look at the distribution of the data itself. So if one thing that you might want to do, depending on what machine learning algorithm you use, is actually normalize the data, right? Here, some of the data is not only normalized, it's very eccentric on some of the size, and in some instances is quite unbalanced. Again, if you look at the event types, as you can see, there's way more examples of no violation versus violation. So we'll see how that plays into some of the metrics once we train the models. There are some other ways to actually show and look at the plots. Again, looking at the correlations, for example, event type and is certified, seeing the negative correlation over here. Just a different way of looking at it. Again, specific distribution of the hours driven. As you can see, most of the data points are between 40 and 60 hours, and then at the very beginning when nothing's going on. Here's just a bit of information of the actual pipeline. So if you want to get more, if you want to read a little bit more on what actually happens in the Spark pipeline APIs, you can take a look at this one. And then you have basically, you're setting up the pipelines themselves. So this is basically going through the different steps. And as you can see, here's my vector assembler. So I'm assembling different pieces because the pipelines API requires this, in this case, to be passed as a vector. And then my actual stages are right over here with the assembler and the random forest classifier being pointed out here. And at the end, I have a label converter, which converts back the results so they're human readable. As I mentioned previously, we have a training set that we're going to do. What we're doing is basically taking 80% for training and then leaving 20% for testing and verifying the model. Once we cache this, we print the schema. And again, in the video itself, I go a little more detail. So if some of this is too fast, you can watch the videos and for all these paragraphs that I'm skipping a little bit more quickly over here. This is interesting. So once we actually have the model trained and we're looking at some of the tables, you can see very quickly, these are just some sample 5 data points. Most of them have been, these are the actual event types here that have occurred, and here's the predicted label by the model itself. So in most cases, it's been predicted correctly, and you have the probabilities or the confidence levels with which it predicted this to be the case. So in most cases, 73%, 81%, so forth. Here we have a misprediction, but it's quite confident that it should be the other way around. Then we go to the actual model evaluation. So first we look at model accuracy. So basically take a look at all the data points and we calculate the accuracy. Now, accuracy is quite high, right? It's at 88%. This is actually quite interesting because I had a different, slightly larger, which had even fewer violations than no violations, and that data set was at some 90-several %. And that was because we had so few data points of actual violations that just scoring it across the entire data set, the actual violations was such a small percentage that the model was mostly accurate. So, if you just scored it as basically no violations for all data points, kind of like when I was showing you with the decision trees visualization, where you just took a fork, you would still be very accurate in your model, which is one metric, but that metric doesn't really tell the whole story. So then we can look at the precision and basically look at how good the model is of actually indicating that a violation has occurred, and that's slightly lower at 87%. This was again with the larger data set, with the more skewed data set, this value was went down to about 70%. And then of course you have the area under the ROC curve, which is a fairly standard way of looking at it, with both indicating being positive of how many violations have occurred versus how many violations have not occurred, and whether the model is good at predicting the both cases. So with that, then we have different metrics. So one thing to do is to determine what are the relevant metrics that you're working with. What is the significance, and does the metric actually tell you the whole story? That's why accuracy sometimes might not be sufficient, and looking at the data set, visualizing it, is part of a data scientist or analyst job at this point, of making sure that you have the entire picture, and then that kind of goes into the whole model evaluation. So here's basically what we're doing is we're saving this model in the machine learning repository. I've got to admit that this is a new API that I've just copied and pasted late last night over a few drinks. but it does work. So what we're going to do next is, once you run to this point, you should have a state model, and here's a sample response that should show you what the model does. And the next step is then to actually look at the model itself. So the cool part, again, what I've mentioned about the DSX, and it's something that, before we had this close partnership with IBM, we didn't have a way to give to our customers a way to easily deploy the models. That's actually one of the biggest struggles on the data science teams. And I would always be asked previously, like, okay, we've got the Zeppelin notebook, we saved the model, but what's the next step? How do we actually deploy it? How do we use it? So here I'm just going to go over testing the model in the UI. In the video, I also show how you can go and actually test the REST point APIs that are being deployed. Because once you actually test the model, then you can publish it, and then you deploy it, and it creates for you a REST endpoint, and then you can reference it as REST endpoint externally, pass in the parameters with a unique token that's actually generated on a 24-hour basis that you get, and then you can score your model. At this point, by the way, before I go on, the model is stored in the DSX cluster, and in the future you'll be able to point it to, say, push this model to whatever server you have for infinite scalability. So if you have very strict SLAs, that's the way you're going to go for it. So now, as you see, once you've gone through the whole thing, you should see in all of your assets this model. It's called event type. You can see that it uses the accuracy as a default metric over here, and it's got the 88% that you saw in the notebook. And I'm just going to do a quick test over here. So let me, off the top of my head, is certified. Let's say no. Payment scheme miles. Hours driven 50. Miles driven, say 2,000. Latitude -3. Longitude, I don't know, say 50. Is foggy? No. Is rainy? No. Is windy? No. Let's see, submit. Boom. So basically at this point it says that there is very low incidence of committing a violation. So let's see what happens. As you remember, there was a strong correlation with weather conditions and having a violation occurring. So what happens if we change this value is foggy to 1? So now the driver is driving a foggy environment. It's still no, but it's much closer, right? So the probability of a violation is much closer. So one thing that you can always implement in your app is what probability the violation is there versus a binary yes or no. But perhaps that's not of an interest of raising an alert yet, but now it's a foggy and is rainy. So let's see what happens. So now you have a definite yes. There's a very high likelihood that a violation will occur. The driver's been driving for 50 hours. It's been very, well, it's been long 2 days almost. So at this point, you should definitely pour over. As you remember, one last thing, I point out that the windy, when we looked at the correlation matrix, the windy wasn't as strongly correlated to having the event incident. So now we can verify this. So probably the actual pie chart of yes incidents won't change that much. So let's submit that one. So as you can see, well, actually it even affected it differently. So so this is a very cool way of kind of playing with the variables that you have and testing the model in many different ways. Seeing, testing different values of what affects it, what doesn't affect it, and sort of looking at your data set, and that will be part of your data science job. The next piece, of course, is to publish this. Let's see if this actually works. We're running on the latest version of DSX 113. Let's see, publish name, trucking demo. Yeah, let's see, publish. So I gotta put some more data to it. So I'm gonna skip that one, but I go over this one in detail in the videos if you wanna take a look. So let me wrap this up with a few notes, and then I'll open up this to any questions you might have. If you want to wait after the public sphere, I'll be hanging out here till 2 or 3 o'clock, and I can answer some more questions. We can talk through some other problems. Again, this environment will be up till about 9 p.m. today, so feel free to play with it. If you're done with the notebook, you can start checking out other notebooks that are there, but make sure you kill that environment so it doesn't crash or doesn't slow down the entire cluster for everybody else. So let me just go through some final notes. Another quote from MIT that I like, that the business value of AI, in this case what we're talking about is machine learning, consists of its ability to lower the cost of prediction, just as computers lower the cost of arithmetic. I really like that quote. It speaks to me in many ways. And there's some questions that I've been sort of compiling as some questions to answer when you're exploring, when you're deciding on, for example, the data platforms that you're going to use, data science platforms that you're going to use, and some of these things. For example, questions to answer: where is our data? Do we have all the data that we need to train these machine learnings? How will we bring more data? Will we bringing some IoT services, for example, HDF with NiFi for basic event processing, and maybe some other tools such as Spark Streaming for more complex event processing, where we'll do the ETLs and transformation of this data. Do we have a 360 view of this data? Some things that you've heard at the keynotes. Can we actually see all the data in our environment? So if the data is, for example, in disparate clusters across cloud and on-prem, do we have access to this data? Do we have the visibility to this data? So we could bring all the data pieces that will be useful to train our machine learning algorithms to eventually make them more accurate, or whatever the metric is going to be, right? Again, what type of development environment? What is the data science platform cost? Is it self-service or managed? Is it integrated with larger ecosystem? So in this case, for example, DSX is very well integrated with HTTP and will become even better integrated in the future. Wait for some interesting announcement in June. Is it open? Is it proprietary? Is it extensible? Can you bring other models, external models? For example, can you bring Anaconda models? Can you push your scikit learn models in distributed way to different nodes? Does it support TensorFlow? Does it support other deep learning models, if that's what you're interested in? Does it support GPUs? Especially if you're running deep learning, you probably want to run all your TensorFlow jobs on GPUs themselves. In the future, maybe you want to consider FPGAs, or if you're running in Google Cloud, you probably want to look at the tensor processing units, which are specialized for those kind of tasks. Is it scalable? Many of the data science platforms are only one node systems that you can vertically scale up. Are the machine learning algorithms distributive? Can you distribute them across different machines, right? For example, with Spark, you can distribute across different nodes. Are you doing this in the cloud, on-prem, or is it a hybrid of the two? Very important here. Does it comply with GDPR? Is there security in place to make sure that all the data is secured wherever you're running? Are all the rules for the data scientists implemented there, so they have access without having to go through all the legal, challenging situations to actually determine, can I use this data? This is actually very frequent. Are you considering serverless computing? And when you do, running, for example, ephemeral jobs on some of the cloud-hosted platforms, are you considering the total cost of ownership? Right? Because it's easy to spin up those data science jobs, but what is the total cost of ownership as you move forward? Does it support high-performance computing? So again, some clouds might have access to older GPUs, some clouds might have access to cutting-edge GPUs, some clouds, again, might have access to specialized hardware. And of course, more questions of where you're developing. Is it in-house? Are you building out a data science team, or are you bringing consultants to help you get started? Are you using APIs and then building out your own solution? Are you using what's generally available APIs for everybody, or bring consultants to focus and build the APIs on your specific corpus of data? Right? What's general knowledge for example, for natural language processing will be different for your data sets or your text data, especially, for example, in legal frameworks. And of course, very importantly, how will you package it? How will commercialize machine learning models? And again, what is the process? Are you making the life of the data scientist easy by just clicking a few buttons, deploying the models, and not worrying and making sure and going back and forth with data engineers, making sure to explain how to actually deploy these models. So all these questions are relevant. All these questions should be at the top of your mind. Well, of course, building your business around AI, another few pointers from Harvard Business Review. Probably don't even have to repeat this, but again, find and all valuable data that nobody else, especially for smaller companies, is important. For startups, if you want to compete, one of the essential points is where do I get my data? How do I get this data that's unique? How is this data that will make my predictions, my machine learning algorithms better than everybody else's? Again, take the systematic view of your business and find data agencies. So perhaps these are data marketplaces that you want to access. Perhaps there's some data that just lies as dormant and you haven't had access to it. So making sure that it's accessible to your team, to your data scientists, making sure that all the legal frameworks are there, and everything's been nailed out, has been done. And again, packaging for the AI customer experience. So that's it. With that, I'll finish. Thank you very much. Hopefully you got some insight. Hopefully it was like a high-level review. Again, this is a crash course. If you want to go more in depth, we have phenomenal trainers that do multi-day training on Spark Basics, data science, and now deep learning. So feel free to reach out to them. We have, again, what I mentioned, HCC or Hortonworks Community connection. Just type community.hortonworks.com. It's also in the links in the sheet. You can post a lot of questions. A lot of have been answered, especially when it applies to enterprises. Again, our solution engineers are on top of many of those questions. With that, I'll open up to any questions you have. If you want to just come up here, that's fine as well. So with that, thank you very much and have a great day. Yeah, so the video clips. So the question was, do I have the video clips, how to publish the model? So when you go to that spreadsheet, you see there's the other tab at the very bottom with the links and shared info. So if you click on that one, there's the link to the IoT and data science trucking demo blog. If you click on it, it will take you to that blog. So again, there are the two videos that essentially go over, let me see. Yeah, there are the two videos that go over what I just did in a little bit more detail. And then they show how the actual models are published and deployed. And they talk about the different REST endpoints interaction, including command line interaction with the REST endpoint. So basically full deployment, publishing, and then I touch a little bit on model management. So once your models are deployed, new data sets come in. How do you make sure that alerts are sent when the model doesn't perform to whatever the metric you specify to? And then finally, there's the video on the IoT trucking demo. I'm sorry, on the NiFi part. So basically, I go over this piece where I show, okay, this is too large again, how the NiFi piece is connected. So what we did is, let's see as it runs. What we did basically is we have different components. Let's see if it's running. Okay. Different components that I should zoom in a moment. Yeah, there we go. So how many of you have seen NiFi already? Just one. Okay. So this is very cool drag and drop GUI interface. And you just configure these different elements. I'm just going through some properties and showing you the Python script code. So this is just a Python code that randomly generates all the possible values in the data set. Here what I'm showing is the actual access token. So within the previous video, there's and in the notebook that you can actually download from the blog, there's a section where you can generate the tokens. So you have these unique tokens for security purposes that get refreshed. Oh yeah, I showed right over here. That's the actual line. So that's the token I copy and paste over here. This can be, of course, automated. So this is the same curl command. It basically goes to the REST endpoint. So in the video itself, there's a REST endpoint. Once you deploy the models, you get REST endpoint. So that was the REST endpoint in the code itself. And now is the module that does the actual decision. So with the randomly generated data in the previous module, it then can decide and basically call the model and say, is there a violation or no violation? And then it reports these violations and saves them to a text file right over here with these put file processors. So this is the normal and this is the failed. Of course, with NiFi, you can connect it to all kinds of IoT devices. There's also this piece called MiniFi, and MiniFi is a very light version. It's written in C, a bit of C++, and that will fit on your Raspberry Pi, on your smartwatches, so any light sensors will do. And then through the NiFi, which is slightly larger, heavier, written in Java, it publishes, and then you could pull the data from all your sensors, all your IoT devices, REST endpoints, social media, web, etc., and create entire data source, push it into your data lake perhaps, or some object storage, and then, or you connect it directly here, and then the data would flow automatically. And then, for example, you could store it for long term, but you could also push it to some kind of dashboarding. So you have dashboarding where you monitor in real time what happens, what are the conditions under which the drivers are driving, and whether I should raise an alert and perhaps call the driver, see how they're doing, see how they're feeling, and tell them like, hey, maybe you should pull over, it's been a long day, or the weather conditions will, that's actually an interesting piece, perhaps the weather conditions will change dramatically in the next 5 to 10 minutes, so now is a good time for you to pull over, because based on these weather conditions in 10-15 minutes, you are in a high likelihood of committing a violation. So those are the kind of things you could do. So again, this is in the IoT tracking demo. So I highly recommend that. And again, more videos on Spark ML Lib if you want more details. And I go over, again, in details over some of the machine learning algorithms I've mentioned today. Any other questions? Yes? In what sense? So the question is, how would we publish these models at scale? So as I mentioned, right now these models are saved in DSX. So for example, if you have 9 node DSX clusters, they'll be hosted there. Soon you'll be able to specify what's the server or service where these models should be pushed to. So however you want to host your REST endpoint, that's going to be there. You're just going to push it there. It's packaged. It's just REST API, so it's infinitely scalable behind a load balancers at that point. Any other questions? So yeah, feel free to watch these videos. I'm going to go turn off the mic at this point, and if you want to just come up and chat about anything, I'll be hanging out here. Sounds good? Awesome. Thanks a lot, guys.